Hi, my name is Miss Townsend. I like math. Let's do some math together. In this video, I'll be going through some piecewise function concepts that we learned in advanced functions. So, we will start with a question like this. So here I've given you a piecewise function, and we know it's a piecewise function because it's a function that is made up of pieces of other functions. So there's three different pieces here, and each piece fits onto a particular part of the domain or the real number system. Oops, we don't need the ruler. So to start with, let's make sure we understand what's happening by doing what I've got over here. So we are just going to find the values, some of the output values on the function. So first I want to find the output when f is -4. So when f is -4, which rule applies? So at the top we have the rule that applies when x is less than 3, but not equal to 3. Then we have a rule that applies between 3 and 6. And then we have a rule that applies above 6. So that's sort of what I'm thinking about. Sometimes it is nice to see that sort of number line drawn out. But so we know that -4 applies to this part of that function, or this piece of the function. So f at -4 would be -4 squared plus 1, which is 17. So now I'm going to find f at 0. So f at 0 is also a number that's less than 3. So I'm going to use the exact same function rule I just did, which is this one. So if I sub 0 into the function, I get 1. So when I input 0, the output is 1. So now it's asked me to find f at 3. So just be, this is 3 is one of the values where one function rule switches to another function rule. So just be careful to make sure you're using the rule where 3 actually exists. So if we look here, that says x is less than 3, not equal to 3. So that's not the rule I can use when x equals 3. When x equals 3, so this equals sign tells me x is greater than or equal to, this is the rule that applies. And of course, that's the rule that says no matter what your input is, your output is just 2. The next one says find f at 5. And of course, 5 fits between 3 and 6 quite nicely. So again, f at 5, we'll use this rule. And the rule is no matter what your input is, the output is 2. Then I'm asked to find f at 6. So again, we have to be a little cautious because 6 is one of the places where the function rule switches over. So we just have to be sure we use the correct function rule. So this says x is less than 6, but not equal to 6. This is the one that says equal to 6. X is greater than or equal to. So this is the rule that applies when x equals 6. So I'm going to sub 6 into that rule. So I get 1 minus 12. So -11 is the output. And then finally, I'm going to find f at 7. So again, obviously that's here. At 7 is greater than 6. So I'm going to use this rule again. 1 minus 2 times 7 is 1 minus 14. That's -13. So that's making sure that we understand the very basics of a piecewise equation. And we're also going to graph this function just so we know how to graph them. Now it's a little hard for me to graph sort of using my tablet pen, so get ready for some really probably very ugly looking graphs, but the concept's what we're looking for, right? So first I have one rule that I have to graph when x is less than 3. So I'm going to use this graph. I'm just going to use it as a scale 1, 2, 3, 4. So x is less than 3 means these x values. And the function that I'm graphing is y equals x squared plus 1. So I'm just going to graph that, and then I'll come back and erase the stuff I shouldn't have graphed. So this is just a regular standard parabola, but the vertex has moved up 1. So there's the vertex. And then regular parabola over 1 up 1. If I go over 2, I need to go up 4. If I go over 3, I need to go up 9, 4, 5, 6, 7, 8, 9. Ooh, it just fits. So this is just me graphing y equals x squared plus 1. This is the part that's not going to be pretty. Oh, look at that. What? Oh, ooh, yikes. Anyway, there's my wonderfully drawn parabola. But of course, it's not supposed to exist everywhere. It's only supposed to exist when x is less than 3. So I'm going to erase, well, I erased the whole thing, but that actually is not okay because it was such a terrible graph. It just doesn't make me happy. Smoother. Oh, kind of smoother. Nope. I don't think I can draw it nicely. If only there was like a math snap to. So anyway, basically at 3, the place where this function like stops existing, we're at a value of 3 squared plus 1. We're at 10, which is this point here. So this parabola, as ugly and terrible as it is, exists everywhere. Oh my goodness, even my arrow went bad. So this parabola exists here. But we put, pretend it's there. I don't know what's happening now. Good enough, good enough. I'll be happy with it. So we need this arrow here because even though I've stopped graphing it, like when x equals here, it exists. I just don't have the grid paper to show it. So I put the arrow to say it continues like this. And then on this side, I need to indicate that when x equals 3, I shouldn't actually have a point on that parabola. So we do that by drawing an open circle. So let's see if I can make this work and not disappear. So there's a nice big open circle where x equals 3. Whew, what an ugly, ugly, ugly parabola. But we'll live, right? It's concept, not execution. Wow. I mean, okay, now I have to draw this. So that is the horizontal line at y equals 2. And I need to draw it between 3 and 6. So here's where y equals 2. So between 3 and 6, is a line like that. Here, it's allowed to be equal to 3 on this line. So I put a closed circle. But here, where x equals 6, I need to put an open circle. So I'm going to nice big open circle, unambiguous. So that is an output of 2 for the value between 3 and 6, but not including 6. And then finally, I've got to draw this. That is a straight line. So you could also think of it as y equals negative 2x plus 1. And that exists when y is greater than or equal to 6. So I'm going to, just because of how terrible this is to draw on here, I'm going to sub 6 in and figure out where that point is. So if I sub 6 into this function, I would get a value of negative 11, which would be here on my graph, and it would be a point because it's equal to that. And then I'm going to sub 7 in. This is another way to graph it. Just make a table of values. If I put 7 in here, then this is negative 14 plus 1 is negative 13. So it would be like this. So basically there's a line really off grid down here like this that represents the third portion. And you can see that I closed the circle here because that point when x equals 6 exists on this line. So that's a terrible looking example of how you might graph and the importance of the open closed circle and the greater than less than thing. So let's look at sort of the reverse scenario, which is where I'm giving you a diagram, I'm giving you the graph, and I want you to write the equation of this function. So we can see that this function has been split into 2 pieces. So I've got the first piece, which goes until 0, and then the other piece which goes 0 and above. So I know that my function is going to be made up of 2 different function rules. So the first rule is this line, and it exists when x is less than 0. So all of these x coordinates which produce this line, this input-output points, they're all 0 and below, and that is an open circle, which is why I used x less than 0. So the second function, which is a much easier function to find the equation of, exists at 0 and above 0. So x greater than or equal to 0. And of course, we'll do this one first. That is the horizontal line where y equals 3. It doesn't matter what x is, so the equation is just y equals 3. And then over here, this other line, let's see if I can find the equation. So I know that there's a y-intercept of 0. And let's see if we can find slope. Doesn't look like I'll find it perfectly, but let's pretend, because, you know, we don't want to, I actually technically didn't make that graph as nice to find the slope, but we'll just pretend you would do what you normally do. This is a slope of down 4 and over 3. So this is the line y equals negative 4 over 3x plus 0. Of course, we would never write the plus 0. And because this is inside of a piecewise f at x function, then we just write what y equals, but it's actually f at x equals. So that's the equation of that line. Sorry, that's the equation of that function and the equation of that line. And then let's do one more example of that, just to make sure we're comfortable with it. Moving over here. Boop, 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 boop. You like how I never edit videos? Because I don't have time for that. So this function is made up of 3 pieces, piece 1, piece 2, and piece 3. So I know that when I set up my function, I'm going to have to make room for 3 different function rules. So f at x equals, and I want 3 different function rules, so a nice big bracket. So the first piece is a nice horizontal line. They're the easiest equations to find. Like this is just the line y equals 3. So I'm going to write that immediately. And what domain does it exist on? Well, it starts at negative 3 and includes negative 3. So negative 3 less than or equal to x. And it stops at 0 and it does not include 0. So that's that first piece, horizontal line from negative 3 to 0. Then I have another short little baby horizontal line at y equals 4. And I've got a closed circle and a closed circle. So it goes from 1, sorry, not 1, that's at 0. It goes from 0 to 1, and it includes both 0 and 1, so less than or equal to in both cases. Then we have this line that has a slope. So we know that it starts at 1 and it goes until 5, but it does not include the 1. You can see there's an open circle there. So that's what that the interval or domain of that part would look like. And then we know that if we extended this, we would have a y-intercept of 0, and you can see the slope is just over 1, up 1, over 1, up 1. So that is the line just y equals x. So you can see that 1 is 1, and 2 is 2, and 3 is 3. So that's the equation of that line. Sorry, that's the equation of that line and the equation of that function. Okay, then let's look over here. So we also talked about the concept of continuity on a piecewise function. So this says, where is this function continuous? So we can see that the function starts below or equal to 1. So like negative infinity is part of that, and so is negative 100. You know, so negative infinity to 1, we're following this function rule. And that function rule is just a lovely quadratic, which would be continuous everywhere. So we know that we don't have to worry about any continuity issues before 1. But we do have to worry about what happens at 1, because we have a function rule that changes at 1. So I need whatever's happening on this function needs to end where this function begins. So what we can do is we can just find what happens at 1. So at x equals 1, this function is going to end at the point y equals 3 minus x squared. So y equals 2. So the top function finishes at the point 1, 2. The function below it, which starts not exactly at x equals 1, but let's find where that open circle is. So it's going to be an open circle at x equals 1, right? We can tell that because of this notation. But what we want is the open circle to be at the same point where this point exists. And we know that this just has a value of y equals 2. That's the function rule. So the open circle I would draw to represent where this x value is for this function is the same point, which means that the left side sort of does this, and then the right side starts here and does that, But on the graph, we wouldn't actually see the open circle at all. We would just see brr, 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 brr. So I'm not actually trying to draw what the functions are. I'm just giving you a representation of what just happened. And that means that it is continuous at x equals 1 because what happened here on the first function perfectly met up with what was happening on the second function. So far, I have a function that is continuous everywhere from negative infinity. Hold on, cleaning up here. Negative infinity to 1, including 1. And then we have this horizontal line. Well, horizontal lines are continuous everywhere. So right now, the only thing I need to worry about, okay, is what happens at 3. Because at 3, we have another function rule change. So does the point where this function ends match the point where this function starts? So I'm going to examine continuity at x equals 3. So here we have an open circle. And that open circle would be when x equals 3 and y equals 2. Again, the output's just always 2. And in this function, we would have a closed circle at x equals 3. And we are examining if it's the same location on the graph as that open circle. So when x equals 3, what happens to that function? Y equals 5 minus x becomes y equals 5 minus 3, which is 2. So according to this function, when x equals 3, there is a point at 2, and that is the same place where this open circle exists. So again, now we have an open circle from that horizontal line, but then we have a straight line that closes the circle. So they meet at the same point. So continuity at x equals 3, it's continuous there. And then, of course, above 3, that's just a straight line. So we know it's continuous everywhere. So where is this function continuous? It's continuous, you could say all real numbers, or you could say from negative infinity to positive infinity. And then here's a similar or related question about continuity, which is solve for k to make f at f continuous. So I want this to be a continuous function. So if I examine, first of all, this rule, that is a straight line, it is continuous everywhere. This is a parabola. Now there's an addition of some number, or it could be subtraction. Excuse me. All that does is move the vertex up and down, right? That doesn't change the continuity of the fact that that function for the second part of the graph is a parabola, which is continuous everywhere. So the only place where this function might not be continuous is at negative 2 when the function's rule change. And I want them to be continuous. My goal is to make them continuous. So k is what I don't know. So I'm going to not look at that first of all. I'm going to look at what I know. I know everything about that first function. So when x equals negative 2, what does this function do on the graph? Where is that point on the graph? Now again, it's going to be an open circle, but it's still where that part of the function ends up. So if I sub negative 2 into the equation, I get y equals negative 8. So this straight line from the top function would end at negative 2, negative 8. Now it would end with an open circle, but as we've seen, if I have an open circle and then the next function starts in the same spot, it fills that circle and gives me continuity. So that means I need the second function, which right now says y equals x squared plus k. I need the point negative 2, negative 8 to be on that function, right? Because at negative 2, I need this function to start at this point. So I'm going to sub negative 8 for y and negative 2 for x, and that'll allow me to solve for k. So negative 8 equals 4 plus k, so k is negative 12. So if k is a negative 12, we have a continuous function because This line will end at the point -2, -8. So I'm just going to represent it in a really, really quick and ugly way. So it's going to end at the point -2, -8. And we've now made it that if we were to graph x squared minus 12, so if we were to graph the function y equals x squared minus 12, that function would have a point here, and then it would do something like this. But because this point fills in that open circle, it's a continuous function, and it's continuous everywhere. Okay, that was a messy and quick video, but I hope it was helpful. Keep doing math.